Hey all, this is a quick lecture on problem solving using the thin lens equation and the magnification equation. Here's our thin lens equation. 1 over DO plus 1 over DI is equal to 1 over F, where DO and DI are the distances to the object and the image, and F is the focal length. We need to keep in mind our sign conventions, which are given down here. We also have the magnification equation. The magnification ratio, capital M, is just the height of the image divided by the height of the object. And if the object is inverted, its height is negative, or if the image is inverted, I should say. Magnification ratio is also related to the DI and DO. It's equal to negative DI over DO. So let's get started with some problems. A convex lens is placed 165 centimeters in front of an object of height 4.5 meters. If the lens has a focal length of 45 centimeters, find the location and height of the image. First things first, I'm going to sketch it out just to identify what's going on. First of all, it's a convex lens. The focal length is 45 centimeters, which means it's 45 centimeters to F. 2F is 90 centimeters. The object is going to be way out here. And I know that if an object is outside of 2F of the focal length, it's going to project a real image between F and 2F on the other side, and it's going to be smaller than the original image and inverted. So right off the bat, I know it's diminished, real, and inverted. But if I want to find the actual location of the image and the height of the image, I need to use the thin lens equation. 1 over DO plus 1 over DI equals 1 over F. And I'm given DO and I'm given F. Here's my DO. Here's my F. So let's just plug in and get our answer. 1 over 165, and I'm keeping everything in centimeters. Centimeters. Plus 1 over DI equals 1 over 45 centimeters. Solve for 1 over DI first. I get 1 over DI equals 1 over 45 minus 1 over 165. We cannot simplify those fractions. Keep that in mind. They don't have a common denominator. So just use a calculator to subtract. 45 to the minus 1 minus 165 to the minus 1 gives me what does it give me? About 0.0162, and the units are going to be per centimeter. That's 1 over DI though, that's not DI, so I have to take the reciprocal of that. I'll do a negative power again on both sides, negative 1 power, negative 1 power, and I get DI equals 61.875 centimeters. And rounded to correct sig figs, it is 62 centimeters. Okay, and that is between F, which is at 45, and 2F, so that aligns with what we predicted. Next, find the height of the image. Well, height is related. The height of the image can be found by looking at the ratio of the object distance and the image distance from the magnification equation. M is equal to HI over HO. It's also negative DI over DO. So we don't need the magnification ratio. Let's just plug in our values and solve for HI. HI over height of the object is 4.5 meters. Keep in mind these units are different, meters. Equals negative DI, which is, I'm going to use the exact value, 61.875 centimeters. Be very careful about units. Divided by 165 centimeters. I need to make sure these units are the same so that the units cancel out. And I can see then my answer for HI is going to be in meters. So HI is negative 4.5 meters times 61.875 over 165. And I plug that into a calculator. I get negative 1.6875 meters. So HI is about equal to negative 1.6875 7 meters to correct sig figs. And it is inverted, that's what that negative sign in the height means, and it is diminished, it's smaller than the original 4.5 meters. So it's as easy as that. Just be very careful about the signs of all of your values. Our focal length is positive because it was a converging lens, a convex lens. However, here's another thin lens practice. Cam is showing slides to his biology class. If the slides are positioned 15.5 centimeters from the projector lens that has a focal length of 15.0 centimeters, where would the screen be placed to produce the clearest image of the slide? So where would the screen be placed? That means we're looking for an image. And if we're placing a screen there, it would be a real image. So we are going to, let's just solve. Let's see. Okay, so here's where the slides are, 15.5 centimeters. So that's going to be DO. This is our focal length. 1 over F equals 1 over DO plus 1 over DI. If we solve for 1 over DI, 1 over DI is equal to 1 over F minus 1 over DO. Let's plug in our values. 1 over DI is equal to 1 over 15 minus 1 over 15.5. And we plug that in a calculator. 15 to the minus 1 minus 15.5 to the minus 1 gives me, it's 1 over 465. So that means that DI is the reciprocal of that. DI is just equal to 465 centimeters. Notice it has the same units as my object and image distance. And if we wanted to find the magnification of the image, magnification is just negative DI over DO. So it's negative 465 over 15.5, which is 30. Negative 30, that is, because it is inverted. So it's inverted. We got the magnification, got the location, and we got that it's real. How about some diverging lenses? A diverging lens is placed 5 centimeters in front of a laser beam to spread the light for the production of a hologram. What is the focal length of the lens if the beam of the laser light seems to come from a point 2 centimeters behind the lens? And what is the linear magnification? So this is a diverging lens. That's a concave lens. And what diverging lenses do is they take parallel rays of light and they spread it out so it appears to come from a focal point on the same side as the light. Here we have diverging lens placed 5 centimeters in front of a laser beam, so we'll call that DO. And the light appears to be coming from this point. Well, let me redraw this diagram. Let's keep this as our focal length. We have our laser beam object here. We have a diverging lens, or an image that is produced. It's going to be upright, it's going to be virtual, and it's going to be within the focal point. So this is my image. So this is my DI, and then my DO is the distance to the laser beam. DO. The laser beam appears to be at a point 2 centimeters behind the lens, so DI is going to be equal to, it's going to be negative 2 centimeters because it's on the same side as the object. DO is 5.0 centimeters. DO is always positive. And we just need to solve for F. Okay, so 1 over F equals 1 over DO plus 1 over DI. That's just equal to 1 over 5 centimeters plus 1 over negative 2 centimeters. So I can do negative 2 to the minus 1 plus 5 to the minus 1 gives me negative 0.3. But again, that's 1 over f. That's not f. F is the reciprocal of that. So I got to take the reciprocal of my answer, and I get a focal length of negative 3.33 centimeters. It's negative because it's a diverging lens, because the focal point occurs on the same side as the object itself. Okay, and then what is the linear magnification? Well, the magnification is just negative di over do. And so that's going to be negative, well, di we said was negative 2. And do is 5. The negatives cancel. So we end up with just 2 over 5, 0.4. And it's positive because our image is upright. It is not inverted because it's a virtual image. Let's do one more example. A gemologist studies diamonds on a light table under a small magnifying glass called a loupe with a focal length of 5 centimeters. That's f. If the image of the gemstones is 185 centimeters from the lens on the same side as the object, determine the linear magnification of the lens. Okay, so we have some lens. We don't know if it's concave or convex, but we know the focal length, f, is 5.00 centimeters. This is our focal point f. And the image is on the same side as the object. So I'm going to say that the object's on the left side. The image is going to be out here, which means it's going to be a virtual image. And it is 185 centimeters. That's going to be equal to distance to the image. But since it's on the same side of the lens, it is a negative value. Now the question is this a concave or a convex lens? Well, from what you know about concave and convex lenses, you should know that for a diverging lens, the image is always going to appear within the focal point if we have a virtual image. But for a converging lens, the image will appear always behind the actual object itself. So this has to be a converging lens, which means the focal point is actually a positive, or the focal length is a positive value. Really, I should draw my focal point on this side. So let's just calculate, well, we want the linear magnification of the lens, but we know that the magnification is just negative di over do. So we're going to need to get do to get the magnification, and we can use the thin lens equation to get that do. So 1 over f equals 1 over do plus 1 over di. We solve for do. Well, let's solve for 1 over do. That's equal to 1 over f minus 1 over di. Plug in our values, 1 over 5 minus 1 over negative 185. This is all in centimeters, or per centimeter, really. Plug it into a calculator, 5 to the minus 1 minus negative 185 to the minus 1 gives me a value of about 0.2, and I take the reciprocal of that to get do. do is 4.87 centimeters. And that should also mesh with what we know. That means our object is within the focal point. So this is our object. This is our image. But that's not the answer. We need the magnification, which is equal to negative di over do. So that is negative 4.87 centimeters divided by, oh, I flipped it. Di is actually negative 100, well, di is negative 185, so it's negative 185 centimeters divided by 4.87 centimeters to get our magnification. The negatives cancel out. and we end up with a magnification of 38. Positive 38, because it's a virtual image, it's going to be upright. It's not going to be inverted. So I hope that's helpful. That's a couple of problems involving thin lenses. Keep in mind that if you're solving problems involving mirrors, all the math is the same. It's just that for mirrors, real images occur on the same side of the mirror as the object, and virtual images appear on the other side of the mirror. Just the locations of the objects, or of the images, are flipped. But everything else is the same. Bye.